And hello, welcome to this video. So again, in this video we're trying to probably refactor or tidy up the dwsim code so that at least it's more modular, it's easier to read. Yeah, so I guess, yeah, what we are trying to do is to get a component, right? And of course this dependency map isn't finalized yet. It has this dependency and it's based on the pump dependency. The pump will then be in turn be based on some property package dependencies. Okay, this property package dependency is it will have input. You will need to determine some calculation algorithm or something like that, and it's supposed to give you all the thermodynamic properties based on two of the intensive properties. For example, pressure and enthalpy, pressure, temperature, pressure, entropy. Okay, so right, this property package, I want to split up its functions like the flash algorithm, the mixture property package. The flash algorithm, I want to use that to sort of calculate based on some inputs, like you give temperature and pressure, you'll be able to calculate entropy, enthalpy, and internal energy, all that stuff, right? So this is the flash algorithm. Okay, flash algorithms here, I think it should be eventually dependent on the equation of state, and this is like the smallest module possible. So each of these branches can be sort of condensed into a class, and each class is supposed to do only one job and one job only, right? So let's just focus down on this equation of state thing. Okay, none of this is final yet. I might redesign any of this, but as a unit itself, I just want to sort of emphasize that, yeah, when we develop code, we can just develop them in parallel. As long as we split them up right, this should be fine. A single phase pure fluid equation of state, alright, it should have a certain input, let's say pressure, temperature, and it should have certain outputs like density, constant pressure, heat capacity, constant volume, heat capacity, stuff like that. And I'm hoping to develop an ideal gas package which implements this interface. Okay, so this interface here, I can probably of course write it in C#, but yeah, it is implemented by various packages like this ideal gas package and this cool props energy package, property package. Okay, again, cool props is a very nice thermodynamic package in itself. It is standalone. Very well done, I think. It's hopefully simple to use. I have not tested it out yet. The other thing I want to try is in the ideal gas package by dwsim. At least if we use it to crack open how dwsim works, and hopefully we can see how the ideal gas calculations work in dwsim. So just a spoiler warning, it's very complex. Again, it's hidden somewhere in those 12,000 lines of code I have shown you before. Right, so okay, on when we started, we were looking for unit operations, and I was looking for an ideal gas property package, right? I wanted to see the PV equals nRT equation somewhere in the code. Unfortunately, if you take a look at this ideal Visual Basic code here, we just see lots of, for example here, we are jumping straight into Raoult's property package. Now Raoult is it's not that simple ideal gas. It's a multi-phase kind of a problem, solubility if I'm not wrong. So I do not see any of the things here, such as, you know, how do we calculate the heat capacity, how do we calculate volume. All of this is just not here. This seems like it seems like many classes underneath they have this kind of a thing, right? So yeah, no luck. I mean, it's no good that I cannot find anything here that deals with volume pressure. I don't see a PV equals nRT equation. I just see a lot of things here. However, there is something I found. Okay. Something I found. For example, if you take a look at these things here, mprops equals property packages auxiliary prop, muni equals property packages auxiliary unifact, mid equals to property packages auxiliary ideal. So this is the ideal gas or ideal whatever property package. So that's one of the things here. Okay. This MID has a HRA mix function. Okay, where is this thing located? It's located under property packages. Go to models, and you'll see the ideal.vb. Alright, so this is the ideal class. It has a HRA mix, and again, fairly confusing to me because again, no comments are here. It just has a variable called MMM, and no comments are given as to what MMM is, so I can't really tell what's going on here. Okay, I can only guess this H is actually enthalpy of some sort, right? I can see R here is some ideal gas constant 8.314. You got to know your stuff, but other than that, I cannot tell what this is. So we're probably not going to find our answers right here. However, we see things like CP and CV here, which are probably the correct what do you call that? The correct variables, which are these are CV is definitely constant volume heat capacity. CP equals is constant pressure heat capacity. Other than that, we don't really know anything. We don't see any formulas here, other than what's already shown here, and it's just confusing as ever. Okay, so okay, after some searching of the code, I found out something like this. You see, I see this thing in a dwsim functions under the property package ideal VB. Right, here is a region called dwsim function. What does this region mean? It means that in Visual Studio, if you click this region thing, you can actually collapse this whole section. So this whole section is like collapsible. Alright, so at least some of the functions were well named, so good job. But yeah, I hope more of these functions are like that. Okay, what is this thing called? It says dwcalcCp isol. Okay, dwcalcCp. Okay, we are looking for something which calculates the constant pressure heat capacity. Okay, so it's well, we take in a phase, we take in a temperature, we take in a pressure, and then that should return a constant pressure heat capacity. So what is this? It will return me.auxCpm phase 1t. Where is auxCpm? auxCpm. If we scroll all the way to the top, okay, scroll all the way to the top, you see this is 1 out of 6. You will just see this is actually the first instance of auxCpm in here, and we know by this function, at least, even though there are no comments, we know what this is supposed to do. It's supposed to calculate some sort of heat capacity here. Okay, and this will be for the ideal gas. Alright, so we are sort of there. Where does auxCpm come from? Well, we'll have to actually look at what this Raoult property package, where does it inherit its classes, functions, all the properties from. It inherits from property packages.property package. Okay, so fortunately or unfortunately, we are going to have to deal with this 10,000 line long code. Okay, this is the property package namespace, and we are looking here, right here, at the property package class. Okay, and it will be inherited by some other classes. 10,000 long lines of code. Alright, let's look for this thing called auxCpm. Okay, auxCpm is a function here. Okay, auxCpm is a function here, and it's going to take some phases here. As you can see here, that it looks like a for loop. It says for each substance in current material stream got phases. Okay, value plus equals. Plus equals means, okay, if we have a value, we will add this this whole thing to the last iteration of the value. And good thing again, this thing is named decently well. Okay, substance, mass fraction, get value or default. So this is actually the mass fraction of the substance. Okay, it will be multiplied by me times auxCpI, substance name T. So what is this thing here actually doing? All right, this is actually the heat capacity, the total heat capacity of a mixture. Okay, total heat capacity of a mixture. And what does that mixture do? Yeah, what is this mixture doing like here? So the mixture here is it's actually adding all the so-called heat capacities of the individual components, and then you weight it by the mass fraction. Okay, that's fair enough. Okay, so what are the heat capacities of each of the individual components? Okay, they will be calculated by this auxCpI. So auxCpM actually is the heat capacity of everything. At least there is a unit kind of a thing here, which is great. Let's look for auxCpI. auxCpI. Okay, auxCpI over here is a overridable function. And if you take a look at this function, this is on line 5147. Okay, at least the search function in Firefox actually helps us. auxCpI here actually will calculate the ideal gas heat capacity. So you'll see this thing called dimID as a current material string constant properties ID, dimdb as string. Okay, it will take this compound prop cache original db. Okay, so something is over here under this compound property cache ID object. This ID object will, if you scroll down a little bit and you zoom into this part, you'll see that there is some kind of correlation for the constant pressure heat capacity right here. Okay, and it's in kJ per kg per mole. Thank you again for writing comments. Temperature is in Kelvin, at least it is shown here. Okay, and then all of these compound properties, all these coefficients will be over here, A, B, C, D, and E. Where are all these ideal gas heat capacity constants from? Okay, after some searching, I found that they are actually inside this XML file right here. Right, if you look for, if you scroll all the way to the top, okay, you will see some things here, like see, ideal gas heat capacity constant A, it will be shown as this, ideal capacity heat constant B, ideal gas heat capacity constant C, all the way to E. So all of these actually stored in an XML database. Right, this is a XML database, very hard to read humanly speaking, so I don't encourage you to read that. As a human, don't read that unless you're a computer. Yeah, I cannot read that properly. So all of these ideal gas heat capacity constants come from there. If this database is a dwsim database, so it's after a lot of searching that I found that this database, all right, this database right here is under dwsim assets thermodynamics. It's actually under this XML file here, and there are several XML files here like dwsim.xml, chemsep XML here. It's a chemsep XML. It's a 3.56 MB, so you do not want to read that, or maybe you do just to see what's inside. And again, if you take a look here, this kind of database is sort of given differently. Okay, you can see this is a chemsep v8.00 pure component data. Okay, again, a lot of useful information here, but it's horribly long to scroll through. I do not want to read any of this as far as possible, but it shows you that all of this data is here. The chemsep data is right here, and it's all stored conveniently in XML files. Okay, good. Question is, how do we obtain this compound property cache object? So again, we have to take a look what this compound property cache thing is. Okay, compound prop cache. Okay, compound prop cache right here is a dictionary of ICompoundConstantProperties. So ICompoundConstantProperties, where is it? Okay, yeah, okay, ICompoundConstantProperties.vb. Okay, this is under the interfaces right here. Okay, ICompoundConstantProperties. Okay, if you take a look at this line, dim constprop as new list of interfaces.ICompoundConstantProperties. So this is right here. Okay, ICompoundConstantProperties is an interface. Okay, it's only an interface which gives you some properties right here. There's an extra properties object. It's a name, case number, formula, smiles. Okay, simplified molecular input line of entry system smiles of this compound. IUPAC number. Chemical structure of this compound is a string. All of these are strings. Molar weight, critical temperature, critical pressure, critical volume, critical compressibility, eccentric factor, Z racket, Ping Robinson volume, translation coefficient, Soaf Rich Kwong, Chelsea the blah blah blah. Okay, 200 plus lines of properties right here. Not something I really want to again look through. Okay, I wonder why interfaces are so long. This is really too much in my opinion. Even classes should not be that long. This is only an interface, but I digress. So this is the interface we are looking for, and you know what is supposed to implement this interface. Okay, what's supposed to implement this interface? Well, again, I did some searching, and a class inside this thermodynamic library actually implements this compound constant property interface. So, okay, you can see this public property constant properties as interfaces.ICompoundConstantProperties. So this constant properties class actually implements. Can you see? Constant property actually implements the interfaces ICompound the constant property interface. Okay. Constant properties as interfaces blah 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 implements interfaces ICompound constant properties. Okay. So this is the class we are looking for, the constant properties class. It implements iClonable blah blah blah, and most importantly interfaces ICompound constant properties. Okay, so this part here is the constructor public sub new and sub. This is a constructor of the Visual Basic class. So what does this constant properties class do? If you scroll down and you look, you will see this part called loadData. Okay, loadData here actually reads things from XML. As you can see here, system.xml.link.xe element. All right, so this part here actually reads the XML data. I can probably study this bit of code a little bit more, and probably you don't want to squeeze everything again inside one single class. It's very difficult to read. Yeah. Okay, but now at least we see where things are going. Okay, this thermodynamics based class contains functionality to read this read all of this information, and not just this information, it also reads the it will also read the where is it? Okay, yeah, it will also read the other things. Let me take a look at auxCpm. Yeah, it will also read everything. Okay, it will read the dwsim right, dwsim things right here. auxCpm, yes. CProps is a ICompound constant properties thing, and it will just start calculating all the ideal gas thingies right here. Okay, and you can see auxCpm actually has a few versions of it. Probably overloads. Okay, these are overloads. That means there's more than one way of using the same function, as long as it's here to as long as it's the inputs are different functions will be called. This is what overloads are about. Okay, assume you know that. Okay, so yeah, you see this thing is actually somehow supposed to load all the data. I do not know where it actually calls the loadData function. Okay, the loadData function will read all the information here, the necessary information, not every single bit of information, I hope. And somehow it will probably somehow it will actually load that in. Okay, where is this? Yes, because constant properties thing is actually shoved under the current material stream object. Okay, so the current materials, I guess a lot of the reading will be done in the current material stream. So at least we have some idea of where things go for ideal gases. Okay, we can look in the material stream file, right? But yeah, again, not ideal. There's just so many complexities. The dependencies are going all over the place. I can't even map them out properly just by looking at the dwsim code, but you know the logic is there. Okay, we want to calculate some heat capacity, but to calculate heat capacity we need some of the properties. Okay, we will have a few classes to read all of this data here, the dwsim data. Yeah, once the data is being read, we can then use this data to calculate the heat capacity based on the temperature. So this auxCpI here is actually a way to calculate constant pressure heat capacity based on the ideal gas, constants, right? So where is this shoved? This is actually shoved under the property packages VB. I don't know why. I would think that there will be a separate class or ideal gas file to actually store this. Okay, but that's how I prefer to design it. I think you don't want to, based on the single property principle, you do not want to design classes like that. Okay, so ideal gas package, at least there's a way for us to maybe implement this interface. Okay, we can actually implement this interface right here. I single phase pure fluid EOS, right? I single phase pure fluid EOS. What is this equation of state do? You only care about outputs and inputs, right? I want a temperature and pressure. I want to be able to calculate density CP and CV, right? So just for the sake of learning how to deal with the dwsim thing, we actually looked at how dwsim actually calculates the CP, just CP only, CP of various compounds, right? So the good thing is that if we use dwsim is that we will be able to use all these databases right here, chemsep, cuprop, dwsim, everything here we will be able to use for ideal gas. Okay, and then we don't have to write code ourselves. We can just copy and paste bits of the code here and hopefully do something a little bit neater. Okay, so yeah, we have some place to start. Okay, and once we know our constant pressure heat capacity, we can start calculating enthalpy, hopefully entropy as well, so on and so forth. Okay, yes, so that's it for this video. Just how to calculate a constant pressure heat capacity of ideal gas already, so have to look through thousands of lines of codes, literally thousands of lines of code, and lots of in the repository. Okay, but yes, let's move on, and we'll try to make a library. We'll try to make a library that is based on a neat library, maybe in C#, but it will of course call some Visual Basic code. It will of course call some Visual Basic code, because it's dwsim, then there'll be other things as well. So once we have this ideal gas package, we can also look at cuprop's property package, and then we can put it in this single phase pure fluid equation of state. Then we fulfill the dependency for property package, and then we can see how we can actually calculate everything else also, like every other property in there. Okay, so this is yeah, this is it. Okay, I'm not going to try and calculate backwards. For example, from enthalpy and pressure, you can calculate all the other things as well. I think we'll start with something simple. Calculate everything from pressure and temperature. That's most intuitive for someone from an engineering standpoint. Okay, so thanks for watching. I'll see you again. Bye-bye.